Okay, so the topic of our video today is one of the four categories of organic molecules. Lipids are one of the four categories, as are carbohydrates, proteins, and nucleic acids. I have a separate video for carbohydrates, proteins, and nucleic acids if you're interested. But today we're going to focus on the category of organic molecule called lipids. So let's get started. Okay, so as we go into our discussion on lipids, lipids are what make up fats, oils, and waxes. Now, lipids kind of have a negative stereotype, a negative connotation to them because we hear the word lipid and we see it's associated with fat and we think it's unhealthy and horrible and zero fat is good. Well, here's a couple reasons on why biologically we need fats. Fats provide energy for cells, so we can break down fats and get ATP energy from them through the process of cellular respiration. Lipids make up part of our cell structure. You might know that phospholipids make up our phospholipid bilayer, the outer boundary of every single cell in our body. You look at this picture right here of an elephant seal. Well, this elephant seal is very fat. It has a thick layer of blubber, which is a great insulator for it. It swims in very cold ocean waters and so it has to be able to keep itself warm. So lipids are very much a needed part of our diet. We just don't want to, of course, overdo it and put ourselves at risk of health effects. So when we look at the cell membrane, here we have the blue double phospholipid bilayer right here in this picture. And our cell membrane, the boundary of every single cell in our body, is composed of a dual layer of lipids called phospholipids. So there's another reason why lipids are just really biologically important. They compose the outer boundary of our cells. And embedded within our cell membrane is another type of lipid called cholesterol. Again, cholesterol kind of has a negative stereotype to it because we see the drug commercials with medications designed to lower our cholesterol. But we need a healthy amount of cholesterol. It gives the cell membrane its flexibility. It prevents the phospholipids from bunching up too much or spreading apart too far. So we really need a normal, healthy level of various lipids. So when we look at the structure of a lipid, I want to start with a small grouping of atoms on the top of the molecule. That's why I call it the head. And this small collection of atoms is what we call a glycerol molecule. And I've just simply shown it as this blue circle. And attached to the glycerol head, will be a couple, maybe three or so chains of what are called fatty acids dangling down from them. And so in this picture, I have two chains of orange fatty acids dangling down, but you may have heard of what it's called a triglyceride. The reason it's called a triglyceride, tri means three. Triglycerides have three chains, three tails of fatty acids dangling down from them. So lipids don't always have two. Sometimes they have more than two chains of fatty acids. Well, this is a very simplistic picture right here. Here's a more realistic picture of what a lipid might look like. This is actually a phospholipid. So not only does it have a head made from a molecule called glycerol, but there's also another molecule called a phosphate group. We'll talk more about that if you watch my cell membrane video. But there's a clump of atoms at the top called the head, and then you can see there are two tails of fatty acids dangling down in this picture. And we mentioned in another video that organic molecules are made from monomers and polymers. And so a polymer is simply just what the overall object is, the lipid. And the lipid is made from smaller parts called fatty acids. And you can even add glycerol to that. Fatty acid and glycerol would be the monomers. Well, let's move on. So how do you get that glycerol molecule? Right there, that's the actual structural formula of the molecule called glycerol. How do you get that glycerol molecule to actually bond with those three chains of fatty acids right there? Well, I hope you remember that there's a chemical reaction where small molecules will bond and make larger molecules, and that's called a dehydration synthesis reaction. with the help of enzymes. They're going to break some bonds and remove water. And so watch this. I just highlighted the water that's going to be removed. Look at the fatty acid on the left. With the removal of water. Now look at the fatty acid in the middle. With the removal of water, this is a dehydration synthesis reaction. And now the fatty acid on the right. Again, enzymes help to break these bonds, but when the enzymes break the bonds and water is removed, notice we now have one really large molecule made from the glycerol on top and 3 fatty acid tails that are dangling down attached to the glycerol. This is again a dehydration synthesis reaction. It's how molecules are built up. So kind of the opposite of dehydration synthesis. Well, how would this large lipid right here, how would this be broken down into smaller parts? Kind of the opposite of a dehydration synthesis reaction is what we call hydrolysis with various enzymes. And look at this, with the addition of water, one of the fatty acid chains has been broken apart. Here we have a second water molecule breaking apart the second fatty acid. And here we have a third water molecule breaking apart the third fatty acid. So hydrolysis breaks molecules down. Dehydration synthesis builds molecules up. So I want to mention, you've probably heard of some fats called saturated and other fats called unsaturated. I want to mention the difference. Here's a picture of a saturated fatty acid. I just mentioned that lipids are made from a glycerol head and a fatty acid tail. Well, some of those tails are what we call saturated fatty acids and others are unsaturated fatty acids. So let's first of all look at saturated fatty acids. Notice how there's a long chain of carbon-carbon single bonds. Anytime you see a carbon bonded to another carbon, there's a single bond in between. Now, if you look on the far left of the picture, yes, there is a double bond on the far left, but that double bond is between an oxygen and a carbon. So if you only look at the carbon-carbon bonds, you'll always see a single bond here. And so what we mean by these fatty acids are saturated. What saturated means is that it's just full with. You know, a sponge can be saturated with water. It just means that the sponge is full of water. So a saturated fatty acid is simply full, or saturated with, is full of hydrogen atoms. And notice how the fatty acid is in a straight line. Because the fatty acid's in a straight line, you know, one fatty acid will typically stack on top of another, on top of another, on top of another, on top of another. And that's why saturated fats typically are solid at room temperature. Okay, as I just mentioned, saturated fats tend to be solid at room temperature. You know, here's 2 examples of saturated fats. Butter on the left, and you may not be familiar with lard because it's kind of been phased out as a cooking oil, but you know, lard is very similar in texture and consistency as butter. You know, in the olden days, people would cook with lard. They'd scoop up some lard, plop it in a frying pan, you know, turn the heat on, let it melt, and then you would have a cooking oil, you know, maybe for making fried chicken or something. But saturated fats like butter, saturated fats like lard are typically solid at room temperature for the reasons I just mentioned. You saw a moment ago the picture of the saturated chain of carbon-carbon single bonds. Because those are typically form a straight line across, you're going to have saturated fats stacked on top of other saturated fats, and nice compact stacking of molecules there makes them solid at room temperature. These also, saturated fats also typically come from animals. So the picture on the left is our cow. Again, butter is made from cow's milk. The picture on the right is, of course, a pig, and this is where lard comes from. Lard is simply pig fat. So now let's look at a fatty acid chain that we say is unsaturated. And I hope you see a few differences in the picture. Well, first of all, we still see a long chain of carbon bonded to carbon. The difference, though, is that we can see in this picture I only drew one double bond, but some unsaturated fatty acids will have more than one double bond in between a couple carbons. But we can see that there's a double bond that exists, and this is going to cause the chain to be crooked. It's not straight across anymore, and that crookedness, I'll mention the importance of that in just a moment, but that crookedness is supposed to be there in the picture. It's not a bad picture or a typo or anything. And the reason we say that this molecule is unsaturated, because of that double bond, there's less space for hydrogen atoms to attach. Remember, carbon needs 8 electrons to be full and stable. If you look at both of those carbons attached to the double bond, they each have 8 electrons. There's 4 dashes attached to the carbon on the left, 4 dashes attached to the carbon on the right. That's a total of 8 electrons. There's no reason to have another hydrogen bonded to either of those carbons. That would give it too many electrons. It already has enough. So this is what we mean by it's unsaturated. Because of that double bond, there's less space for hydrogen atoms. You might know that the unsaturated fats are the ones that are typically better for you. They're not as unhealthy, I should say. So if you try to limit your saturated fats and maybe substitute some unsaturated fats for those of you who are trying to be a little health conscious. So unsaturated fats are typically liquids at room temperature, and the reason is because of that crookedness that you saw in the picture a moment ago. Because of that double bond, it makes the chain of carbon-carbon bonds a little crooked. That spreads out the molecule, so that way one unsaturated fatty acid doesn't really stack on top of another one very well, and that makes the molecule spread out, makes them more liquid at room temperature. So examples of unsaturated fats are typically plant oils. You know, for instance, you may have heard of coconut oil. I'm sure you know coconut is a fruit, grows on trees. Another example of an unsaturated plant oil might be olive oil. You know, we have red olives on the left, green olives on the right, but again, olive oil comes from olives, which grow on trees. So these are plant oils. Unsaturated fats, again, typically are the ones that are healthier for you. So if we just kind of put a picture of a saturated on top and an unsaturated fatty acid on the bottom, if we just count up the hydrogens really quick, and you can see the hydrogens being counted, and 18 in the saturated fat on top. But because of that double bond, there's less room for hydrogen to attach to the unsaturated fatty acid on the bottom, only 16. So that double bond, as I said earlier, is going to reduce the need for more hydrogen atoms to stabilize the overall molecule. This is what we call an unsaturated fatty acid on the bottom, and on the top it's what we call saturated because it's full of hydrogen. So one of the applications of discussing lipids I want to mention is that normally blood flows freely. In this case, you see some red blood cells flowing through an artery, so your heart's pumping red blood cells around. However, a person could have high cholesterol levels in their blood, and over time, you might get this buildup of cholesterol, this buildup of plaque, and it can harden and form kind of like a dam in a river. And I hope you see what's happening now. As the red blood cells continue to flow through the artery, they're kind of getting trapped and clogged by that wall of cholesterol there. And so a normal, healthy, open artery might be reduced 50%, like you see in the picture. This is going to reduce circulation, cause blood clots, and could even cause high blood pressure. It could lead to stroke, lead to heart attack. So you really want to watch your cholesterol levels, especially as you get older. And so the medical condition that I just referred to in that animation right here is called atherosclerosis. And so you can see on the top a normal artery, nice and open. In the bottom of the picture, we have an artery that's been closed maybe 50–55% with a buildup of that yellow plaque in the picture. So this comes from a lifetime of bad habits. You know, this doesn't happen because you eat McDonald's and you supersized your French fries on a Thursday night. This happens over a lifetime. So you really want to start to, if you have a history of this in your family, or if you have some signs of the early signs of this, you may want to start talking to your doctor about some different lifestyle choices you may want to consider. And if you are having your blood cholesterol levels checked, here's a little table that might tell you whether or not your cholesterol levels are high. If you're on the borderline of being high, hopefully you're in the less than 200 range. That's our desirable level of cholesterol. So there you go. If you're in my biology class, pause the video and answer these questions. I'd love to check them for accuracy either before school or after school one day. Go ahead and pause the video. Good luck.